Hi, I'd like to welcome you to the talk today in the TDAI invited seminar series. Today, we have Dr. Cecile Viboud is our invited seminar speaker. Dr. Viboud is a senior research scientist in the Division of International Epidemiology and Population Studies at the Fogarty International Center at the National Institutes of Health. She received an engineer degree in biomedical technologies from the University of Lyon in France, a master's of public health, and a PhD in biomathematics from Pierre and Marie Curie University in Paris, France. Her research focuses on the epidemiology and transmission dynamics of acute viral infections, and she works at the interface of public health and computational modeling. Her research has advanced both the methods and the application of infectious disease models and the science that it informs, particularly for influenza. More recently, Dr. Viboud has focused her efforts on coronavirus transmission, and she's here to talk to us about that today. Dr. Viboud, it is a pleasure and an honor to have you speak here with us today, so thank you very much.
Oh, thank you, Laura, for the very detailed and kind introduction. And for the invitation. I hope you're beginning to see my slides. Yes, I'll take that as a yes. Right, so today I wanted to share some work on COVID-19 that we did over the past year, and really learning from experience in the US, China, and South Africa. And obviously, COVID-19 is still with us and we're still learning, and sometimes it feels like every day is something different. So a lot of this work is in progress. And so we're also quite hopeful to get feedback on it. So in the first section, I will talk about disease burden and in particular mortality studies to look at both the direct impact of SARS-CoV-2 on deaths, but also the indirect consequences of the pandemic. And there's been a lot of talks about potential increase in suicide, opioids during the pandemic, as well as people averting the healthcare system because they were scared of being infected. And so that this would have a detrimental impact on overall health in the population. But there have also been interesting papers pointing at the positive impact of the pandemic, and in particular, the social distancing interventions. By decreasing contact, we also decrease the probability of transmission of a range of diseases. And clearly, circulation of a lot of pathogens has plummeted in 2020. So that would also affect mortality in a good way. And so we're going to look at data from the US and South Africa to look at some of those patterns. And then in the second part of the talk, and that's very much work in progress, I'm going to talk about the spatial dynamics of COVID-19 and contact patterns and how some of those affect transmission rates. So starting with mortality data, a metric that we epidemiologists like to look at is the idea of excess mortality, so that the mortality above a seasonal baseline or a historic expectation for what mortality would look like in the absence of a pandemic. And this is an approach that we've used for many different pandemics in the past, including the 1918 flu, the 2009 flu pandemic, but also that's used typically for heat waves and any kind of major perturbations. And here on this slide, we're looking at mortality statistics from 3 different jurisdictions in the US, just to give you a flavor for how heterogeneous the mortality patterns have been in 2020. So on the left, we're looking at the US as a whole. In the middle, we're looking at New York City, so kind of the poster child for this very brief and intense epidemic in the spring of 2020. And on the right-hand side, California, which had a quite interesting pattern of almost escaping the pandemic for quite a bit, but then got caught up later on. And so the different rows represent different age groups, so from youngest to oldest here. And again, there you see a lot of heterogeneity. If we focus for a second on the left here and the sort of middle age group, we see the 3 peaks of the pandemic. This is here the end of December. So we're now in the end of the 3rd wave of the pandemic. But that's sort of the traditional COVID-19 patterns of 3 waves. But if you look at the 25 to 44 years old here, you do see there's a substantial increase in mortality. This is here total mortality each week in the US. However, it doesn't follow the trajectory of the pandemic, right? We don't really see 3 different waves there. And it's, even though it's an age group that tend to have relatively few deaths, this is quite a rise of a baseline. And then in contrast, in people under 25 years of age, we don't see much of an impact. The red line is just because there's lag in reporting vital statistics. So the red line is a model where we take into account those reporting delays. As I said, here in the middle, we have the New York City epidemic, very, very emblematic, very sharp increase, short-lived because it was well controlled. But just to give you, and here what's striking also is that you do see this sharp increase in the young adults as well. And just to give you some context, in New York City, we also have really, really great data from the 1918 pandemic, and we can use the same statistical excess mortality approach. And there we find that the fall wave of the 1918 pandemic, which was the more lethal wave, had a death rate of about 5 per 1,000. And COVID-19 just in the spring here had a death rate of 3.8 per 1,000. So lower, but it is the same order of magnitude, right? So it is kind of the same scale as the 1918 pandemic, although it was controlled there. So obviously it would have been much more severe if it hadn't been controlled. And then on the right-hand side here, we see California. Interestingly, again, if you look at the older age group where really not much is happening above expected pattern at the beginning of the pandemic, and it's really the 3rd wave that really is an issue, but a big rise in young adults as well. So the idea there is to try to really understand some of those different rise and parse out what's directly attributed to SARS-CoV-2 infection and perhaps not coded in death certificates and missed by official statistic versus what's the indirect impact of the pandemic and the interventions. And something very useful there is to look at to use the variability or the heterogeneity in mortality pattern across states to try to reconstruct those direct and indirect patterns. So here we see those weekly total mortalities on a weekly basis for 6 different states and in the US. And then the green line is the seasonal baseline, which, as I said, is our expectation from a seasonal regression model for what should have happened if COVID had not circulated. And then the COVID-19 pandemic impact, both direct and indirect, is just what's above the baseline. And so the first thing we looked at here to try to understand the heterogeneity is to try to say something about infection rates and severity. So what we're looking at here on the right-hand side is this excess mortality rate ascribed to respiratory deaths. So that's the most specific indicator of the COVID-19 impact in the different states of the US versus the attack rates in the different populations. So that's measured by seroprevalence surveys that the CDC is conducting every other week in most states and has been doing so for quite a while. And you can see that there's quite a range of prevalences, and this is at the end of November or mid-November, because there's a delay, of course, in getting seroprevalence data. But you see that there's a range of attack rates here, but also a range of excess mortality rate. And the slope on this curve represents the infection fatality ratio, the case fatality ratio, right? Deaths divided by infections. We can see that on average, it's around 0.7. Through this data set, which aligns with what's been published using other approaches. The case fatality rate is something that's very tricky to measure, but that's used a lot in mathematical simulation models. So that's why it was quite interesting to look at here. We see 2 outliers here, New York and New Jersey. We think that those have just higher mortality, case fatality rate just because the pandemic was so intense. And also it was earlier in COVID-19, so treatment of patients was not, and management was just not as good as it has been later on in the pandemic. So if the healthcare system is overburdened and if you don't really know the disease, then your case fatality rate is going to be higher. So as I said, we're really interested in understanding the direct and indirect impacts of the pandemic. So we can look at different causes of death, and those are deaths that are listed as the underlying condition in the death certificate. So it's thought to be the really proximal cause of death. So here we're looking at 6 different causes. Again, the one in the here for respiratory illness, that's our most specific indicator of COVID-19. And we can look at the synchronicity between those different causes of death and our indicator of COVID-19 to try to tease out the direct and indirect impact. So right away, what you can see is that for Alzheimer, you see a shape that mirrors that we see in respiratory illness, especially in the first wave and second wave. We also see a sharp spike in heart disease that aligns with the first wave of the pandemic, and in diabetes, we see both first and second. Interestingly, we see a rise in what we call unnatural or external cause of death, and that's suicide, opioids, accidents, and any deaths from violence. And so that rise represents about 23,000 deaths in the US over a 7-month period. So that's quite significant. But interestingly, if you just look at the timing of those deaths, it doesn't look anything like our indicator of COVID-19, right? So it's strongly suggestive that those are purely indirect deaths. And so one thing we did is we tried to look at whether those rises in deaths were correlated with perhaps interventions. And so there are very good indicators of the strength of interventions in different states and over time. However, we don't see any correlations there. The best thing that explains those unnatural deaths is just how much of a problem there was to start with in the different states. So states that had a big opioid, suicide, etc., and violence rates, mortality rates just had a high increase during the pandemic. And so this is just to show a little bit more this idea of looking at synchronicity between the different time series. The red here is the COVID-19 respiratory mortality, and then the black line are mortalities from the other causes of death. And so for synchronicities, there are a few different approaches we looked at to try to quantify exactly how synchronous those time series were. So the first one is to look at it in a geographical fashion. So you're wondering whether states that had high COVID-19 mortality also had high mortality from diabetes, ischemic heart disease, or Alzheimer, etc. And so that's a geographic argument. And then the other idea is to look at how much correlation there was between respiratory deaths and diabetes before the pandemic, and whether that correlation or synchronicity increased or decreased during the pandemic. This is what we're looking at here in this easy graph. I'm just gonna walk you quickly through it. But basically we're looking at different causes of deaths here. And in black here, this is the null distribution of correlations outside of the pandemic period. And then the triangles represent the correlation during the pandemic. And we can look at it for different states as well as the US as a whole. And so when the triangles appear in red here, it means that there are significant deviation over the null expectation. So basically what you can see is that all-cause mortality became more synchronized with respiratory mortality because of the pandemic period. We also see a similar pattern in Alzheimer, not in every state, but in a majority of states, diabetes as well. Cancer, interestingly, if anything, we see a decrease of cancer mortality during the pandemic, and the correlation, again, if anything, decreases during the pandemic. So we can't really assign any direct impact of COVID-19 on cancer. We see a slight change in cerebrovascular disease, and for unnatural causes, again, opioid, etc. Again, if anything, we see a decrease in correlation during the pandemic. So in summary, we think that there is a direct impact of SARS-CoV-2 on both Alzheimer, diabetes, heart disease, and cerebrovascular disease that it's perhaps not recognized, but there is no direct impact on cancer and unnatural deaths. So just to try to summarize a bit what's going on, and also to look at different age groups, as we've seen in one of the earlier slides, there's a lot of heterogeneity in how different age groups responded to the pandemic. So here in this table, we've tried to compare our estimates from excess mortality approaches with the official COVID-19 statistics, which are in the middle of this table. And so then we can calculate the percent of total deaths during the pandemic that are ascribed or captured by official statistics. And then we also run a model where we try to explain weekly excess mortality as a function of both COVID-19 intensity and the strength of intervention. And that's the idea, to try to parse out of how much of a direct impact versus indirect impact there is. And so perhaps the most striking finding here is that, this is often portrayed as a pandemic of old age and people with chronic conditions, but we have a lot of under 44 years old that died during the pandemic, 21,000 here estimated from this model. Only a third is captured by official statistics. And so our regression model agrees with the fact that there's only a third of those total deaths that are synchronous with COVID-19 trajectory. So we're not necessarily missing by lab testing a lot of those deaths. But what's striking is that 64%, the remainder, right, are due to the indirect consequences of the pandemic. And we think this is where most of the deaths from suicide, opioids, et cetera, are happening. It's too early to get statistics by age and cause of death. So, it's an hypothesis, but generally those deaths from external causes tend to occur more frequently in young adults. And then as you get into older age group, more and more of the deaths are captured by official statistics, but also directly attributed to COVID-19. So that in the very old age group, most of the excess mortality that we see during the pandemic is COVID-19 infection, a SARS-CoV-2 infection. This is not indirect impact of the pandemic. So we see that, we have definitely a very large mortality impact of the pandemic in the US, much more so than in other countries around the world relative to our population. And 82% of that impact is due to the direct SARS-CoV-2 infection, which I think aligns with the fact that it has been very difficult to control in the US. What's interesting is that we also see substantial increase in deaths from violence in general. And that those deaths are most pronounced in states that had a problem with those deaths in the first place, rather than with the strength of the lockdown, for instance, in different states. So you can't really equate lockdown intensity with increases in those deaths. We think that 2/3 of the mortality in individuals are those indirect consequences of pandemic interventions, and not necessarily the week-to-week changes in lockdown, but perhaps factors that are more difficult to quantify, such as despair, anxiety, or just and that might accumulate over time. And we also see an increase in mortality from heart disease, Alzheimer's, diabetes, and cerebrovascular disease that are not coded as COVID-19, but we think are at least in part due to COVID-19, so undetected infection, just because of the timing of those deaths. And again, a little bit of context overall at this point in the study. So there's a bit of a lag in those data. So that was for the end of November, where we were at about 350,000 deaths in the US. Right now we had 500,000. But that's 24 times the impact of the 2009 influenza pandemic, which was a mild pandemic event. It's 6 times the impact of a severe flu season. And overall, at the scale of the US, it's about 20% the impact of the 1918 flu pandemic. Obviously, this was just true on November 30th, but deaths keep accumulating. So those ratios will keep changing. So because we've seen so much heterogeneity in the US, we've also looked a bit at patterns in other countries, and there's a ton of heterogeneity across Europe as well. Countries that have seemed to control the outbreak very well and have very little rise in excess mortality, for instance, Denmark. Those tend to be generally smaller countries. So heterogeneity should not be remarkable or surprising. But perhaps what sets the US apart is the impact that we see in young adults. And in particular, those indirect consequences that are not seen in the European data. So we also, because we are at the Foguet International Center, so this is the international arm of NIH, so we're really interested in looking at data outside of the US. So we have long-term collaborations with a number of countries, including South Africa. So with South Africa, we've been looking at their hospitalization records. Their mortality data is not quite available in real time. And trying to think also about the same aspects of direct versus indirect impacts of the pandemic. So here we're looking at trends in respiratory admissions in South Africa. The pandemic is on the right-hand side of those graphs for 4 different age groups here. And so you can see that only the adults here, 20 to 49 and over 50, really had an increase of a baseline. The blue being the baseline, the black being the observed weekly admissions, and then the red line is the confirmed COVID-19 cases. So in South Africa, the epidemic had a very clear pattern of 2 waves, so which you see in this older age group. The patterns are very different in children, and if anything, there's been much fewer admissions for respiratory causes than usual. And this is in part due to the fact that there has been very, very little circulation of any respiratory virus infection in South Africa, especially during periods where the lockdown were quite strict, which are the red areas on this graph here. And what's quite interesting also is that in the more recent, the second half of 2020, as interventions were relaxed, they've seen resurgence of respiratory viruses, in particular RSV, which explain this bump in respiratory admissions here in young children. We can also look at variability across regions of South Africa. And there is some, although I would say not quite as much as in the US. There's also quite a bit of variability, it seems, in attack rate. And just interestingly, so Western Cape has this very big city of Cape Town there, and right at the tail end of the first wave, they did a sero survey. I mean, it was not a ton of people, but it was quite representative, and they found 40% attack rate in the community, 35% in children, but 40 plus in older people. And so at that point, our collaborators in South Africa were like, oh, we have probably reached herd immunity. This is great. We're not going to have to worry too much about COVID-19 anymore. And yes, just a few months later, unfortunately experienced a resurgence of the second wave. And so what we're trying to understand now is whether they just didn't have enough immunity after the first wave. 40% is a bit low, and we think it's also quite patchy across the landscape of South Africa. And also we have resurgence of a different variant. And so we want to understand what is the risk of reinfection between the first and the second wave. And to sort of echo the analysis that we did in the US here, we also look at admissions for non-COVID, but other respiratory conditions, as well as trauma and fracture, heart disease, and diabetes. Here in this South African data, the different colors represent different age group. And what's quite interesting is that all of the non-respiratory causes have remained depressed compared to baseline in 2020. And the question is, if you have fewer people coming from diabetes and potentially their regular checkup, are these people who are then going to die and perhaps be reflected in mortality statistics? So fewer consultation might translate into higher death rates. But it's a bit too early to look at that. So in the I'm doing good with time. In the second part of this talk, I will switch to a slightly different subject and talk about contact patterns and transmission rates. And so I'm going to focus on 2 types of study. One is a collaboration with Dr. Yu at Fudan University. So throughout the pandemic, we've done a lot of work on the pandemic in China because they've accumulated quite a lot of interesting data. And then I will talk a little bit about contact patterns in the US. So starting with China, back when we started working with Dr. Yu in February or March 2020, they were really interested in trying to understand how the different lockdowns across China affected contact patterns. And so they did really interesting contact surveys. So those are surveys where you ask a randomly selected sample of the population for how many contacts they had and with which age group. And so they did those surveys in both Shanghai and Wuhan. I'm only showing Shanghai here. So Shanghai, big city, very modern, lots of contacts, lots of people. And so this is contacts at baseline. So this was done actually in December 2019. So in these contact matrices, you have the age of the interviewee versus the age of the contacts. And the darker colors represent more contacts. And that's on a daily basis. And those are very typical contact matrices in that you get lots of contacts within the same age groups across children. Those are school-based contacts. Then you get this sort of square area here, which is sort of contacts in the workplace. And you get those diagonal contacts here, which are contacts between parents and their children. So that's the kind of a typical contact matrix you see, at baseline in a lot of places. And then they were very good in getting their act together and running those contact surveys right in the middle of the outbreak and the lockdown period. And you can see that first there's much fewer contacts. So in Shanghai, contacts decreased 7-fold. In Wuhan, they decreased 9-fold. So a huge decrease in contacts. And you can see also that all of the kids' contacts are gone because there's no school, as well as the square part here representing workplace contacts are gone too because people don't go to work. I mean, this was a really tough lockdown. And the matrix on the right is the difference between the two, so what you're losing during the lockdown period. And so this is very detailed data on contacts. What people have been using a lot during the pandemic is some sort of proxy metric for contact, which is based on mobility indicators, where people follow based on your GPS where you are. And this is the time series of mobility for Shanghai. And you see here the beginning of the lockdown. So in gray, we have a regular year. And then here in yellow, it's 2020. So there's a big mobility drop here, which aligns with the overall decline in contacts. However, those are very, very crude data. There's no age breakdown, for instance, here. So if you can have age-specific contact matrix, it's much better. And then we use those contact matrices to try to understand what would be the dynamics of the outbreak and the different contact behaviors. So here we are showing the dynamics of, in red, of a full-scale outbreak without any control, with a baseline reproduction number of 2.5. And then two different control scenarios where we stop school, so there's no school in blue. And then in black here, slightly different flavor of school closure. There's no school, but you could still have other educational activities. So basically you swap out some of those diagonal for schools. And you can see that closing school helps. However, the total size of the outbreak doesn't really change that much. It does change, however, the size of the peak, which might be quite important for your healthcare system to be able to cope. So since then, we've also done a little bit more of the contact surveys. So this is a timeline of the outbreak. Again, sorry, I'm not seeing my full screen here. Let me see if I can. Yeah, so this is in Shanghai again. So here we have the typical outbreak in January, February 2020, the lockdown period in gray. So the first two surveys were done here at baseline and during lockdown. And then since then, our colleagues did a third survey in the post-lockdown period to try to understand how contacts rebounded after interventions. So we have those matrices here. And you can see that between the outbreak lockdown period here in the middle versus the lockdown period, the post-lockdown period, there had some contacts have come back. However, it's clearly not as intense as it was at baseline here, if you compare with the top. And so, but the question is, are these contacts here in the post-lockdown period enough to spark a new outbreak? And so here you see the observed data from Shanghai, which are so the number of cases in blue. But what's quite interesting there is that all of the cases have been imported in this time period. They have not sparked a full-scale outbreak. It's not just because of depressed contact, it's also because China is really, really good at contact tracing, and they've had really good interventions. But since we have those contacts in the sort of relaxation phase, we can look at what would be the probability of sparking a new outbreak. And those graphs show those probability measured by the reproduction number. And so here in blue, you have the reproduction number for contacts that align with the lockdown period. And in red here, you have for the late spring rebound period. And on the x-axis, you have the baseline R0 for pathogen you're looking at. So if we're thinking of COVID-19, we're probably at a baseline of 2.5, right? So here in Wuhan, in the post lockdown period, the effective R0 would only be 0.7, right? So that's not enough to spark an outbreak. Only if your pathogen had a very high baseline R0, you would be able to spark an outbreak with these types of contacts. In Shanghai, contacts are still quite depressed, so there's no way you can start an outbreak. However, in Shenzhen, for instance, you would have enough contacts, a little bit more maybe to start an outbreak. So there are differences also between Chinese cities in how they responded to lockdown and how they rebounded. So this was for China. We've also been quite interested in understanding contacts in the US as well. In the US in general, we don't have those very, very nice contact surveys. I mean, there's a good group at UC Berkeley that's doing a little bit of that, but really nothing on a sort of national scale. And so we have to resort to other types of proxy. So as I said, a lot of people have relied on sort of this GPS-based metric of mobility. And so we've been working on this with Matteo Cinazzi and Alex Vespignani at Northeastern University because they've been really good at just extracting a lot of information from some of those data sets. So here we're looking at one of the many data sets that are available, and that's called Cubic. Again, one of those companies that just sells some of this GPS data. And so what Matteo has been able to do is to not only look at measures of mobility, but also to look at true contacts. So basically, you're looking at how many people are within the same 5-meter radius for 20 minutes, 30 minutes, 40 minutes. And that's a measure of contacts. If you're really, really close to each other, then you're probably talking to the person, etc. So here is an example. I'm showing data from the greater Seattle area. And we can see here patterns in mobility and contacts throughout 2020 and throughout January 2021. What you can see here in black is the indicator of commuting. So that's recording where people live and where they work and how that changed over time. And that just crashed after the lockdown period. So the lockdown period in the US is sort of mid-March. And that has really remained stable since then. People have just kept teleworking since then, and that really hasn't rebounded. And interestingly, we've looked at this in 300 big cities in the US. That's very, very consistent across the US. So certainly that particular indicator doesn't explain heterogeneity in COVID-19 dynamics across the US. But we can also look at contact duration, which is here the purple line, or a number of contacts here in blue. We can also, for every type of this measure, you can also, look at them either as an absolute metric, which you see here in red for contact duration, or as a relative metric. And relative is just relative to baseline period before the pandemic. And the relative metric we find is probably the better measure here because it sort of scales everything to the same thing. And then more traditional metrics around travel and mobility. So we see here travel in green, crash after the lockdown, came back a bit during the summer, and then down during the fall. The two gray lines here on the right are Thanksgiving and Christmas. And you do see that travel picks up. I mean, as we've been hearing a lot in the news, but interestingly, of all the contacts indicator, it's really contact duration that changed. And again, that's something that we see across the US. So it's not that people necessarily met more people, but that's they met them for longer on average. And the top here just represent the COVID-19 dynamics just as a reference, and this is for Greater Seattle. So Washington State has been really, really good at controlling COVID-19. So they had a tiny wave in the spring, a bit of resurgence in the summer, and most of their impact in the fall. And the light blue here represent the estimates of the reproduction number over time. And you see two small blips here during just after Thanksgiving and after Christmas. So something else that's been changing quite a lot in the US is travel, both short range and long range. And so this is looking at a different data set, which is called SafeGraph, where we can split mobility based on whether it's short range. And here we're taking travels that are below 120 kilometers. And we use this scale, so that's maybe about 70 miles. And we chose this cutoff because that's the sort of the signature of commuting patterns in the US. Beyond that, it's not your regular commuting, it's more traveling for fun or for work, for business, but not for going to the office every day. And here we're looking at pre-pandemic on the left, the lockdown period in April, and then the rebound, summer rebound in June. And you can see that there's been a little bit of a change in the short-range travel pattern, a decline of about 30%, but really not that pronounced during the lockdown. At the bottom here, you see the longer range travel. So it's very hierarchical across the US, right? People tend to be drawn by big cities. But that really declined dramatically by about 60-70% during the lockdown period, and rebounded some in the summer, but not entirely. And so we were interested in trying to combine all of this data to see if they could explain change in transmission rates across the US, so over time and over space. So we're looking here at all metropolitan areas in the US. So we're using a census-based classification, which is called CBSA. And typically a CBSA is 1 or 2 counties. And a few CBSAs are very many counties, such as Washington, DC, New York City, and Atlanta. And we can see the CBSAs here on this map, which are scaled by population size. The dots that have a red circle here are the CBSAs for which we are able to estimate the transmission rate, so RT over time. And those tend to be the CBSAs that have more cases and that tend to be bigger. So of the about 900 big cities in the US, we can estimate transmission rate for about a third. So that's still a pretty good sample of 300 locations. And in this graph here, this heat map, this is just to remind you of the huge heterogeneity in COVID-19 dynamics we see across the US. This is here sorted by state, by the number of cases throughout September. But you can see that some states in the northeastern part of the US, New York, New Jersey, had really more of their cases in the spring of 2020. The southern part of the US, Louisiana, Florida, Arizona, more in the summer. And then here, we don't see the third wave, but the third wave was really much more widespread throughout the US. But there's quite a bit of, again, heterogeneity, both over time and space, which we hope can help us tease out the effect of these different covariates. So we estimate a reproduction number in each city. I'm not going to go into the detail into how we do that, but just to say that you can think of the transmission rate as a filtered view of the incidence over time, and the size of the filtering window is based on the distribution of the serial interval. So it's a relatively short-term filtering or smoothing of your incidence time series. And we're trying to explain the transmission rate in each location and time point as a function of all of those mobility and contact indicators we've talked about earlier. And what we have to consider is that there might be lags between mobility or contacts and transmission rate, because it might take a while for transmission to just build up. So we're also testing different lags between those predictors and the outcome. And so we're using a brute force approach where we're trying all possible combinations of the predictors here, and we're looking at AAC. So what we find is that the indicators that measure contacts more than mobility are typically better predictors of the production number. The AAC declines sharply as soon as you get a contact-based indicator. And we have here the best model for this RT, and this is looking at data until the end of January. What we see is that we find a lag of 25 days between contacts and rise in RT. And we think that part of that delay, which is actually quite long, includes delays in reporting. I mean, it takes a while for someone to be infected, but also to get symptoms, if the person is going to get symptoms, and then to reach the healthcare system, and then for the test to come back. So we think that, is built into this delay. And then, there's probably a delay that's due to the transmission process itself that's built into these lags. So we also try to see whether there were city-level effects. So we included demographics. We also included random effects for cities, but those tended to be quite small. So we don't see any, particular difference that might be city-driven. And so here we don't consider the impact of masking. And so we're going to try to address that in the next step. Even if two people are very close in space and talk to each other for 2 hours, if they are masked, and they were masked in September but not in April, that might really decouple the relationship between contacts and transmission. So we would want to think about that. And then, as we get into 2021, there's really definitely a lot of immunity that is building up in the system and that is not included in this analysis. So we're thinking of ways to include it by just using cumulative incidences or other proxies. But if we can find a model that's a good exploratory model of RT with a good lag, then it suggests that we might have some predictive power there. If we can measure contacts at time t, then we might predict RT at the end of the month. And so to end, I'm going to just show a few slides on a parallel analysis we've been doing with those RT estimates as well as the daily incidence to try to understand the spatial structure of COVID-19 in the US and whether we could see any signature of diffusion across the territory. So what we're looking at here are what ecologists call mental correlation or mentallogram, but this is the correlation in here daily transmission rate as a function of distance. On the right-hand side, we have the same thing for daily incidences. And for ecologists, you get very excited when you see a gradient here of correlation declining with distance, because that's a signature for a traveling wave or a diffusive pattern in your disease. And so we can look at this for all locations in the US in blue or just the eastern seaboard. And so what we see is that there is quite a high correlation actually overall, around 4.6 between both daily RT and daily incidence throughout the US. But there is also a strong gradient here, especially in daily incidences. And so that suggests that there is a diffusive pattern here in COVID-19 infections. We were also interested in looking at how that changed over time. So we can look at those signatures at different time points. So we're looking here at 2-month sliding windows with the darker colors represented earlier time period and then the yellow representing more recent time periods, so January 2021. And you can see, I mean, there are slight differences between RT and incidence, but generally it starts high. During the lockdown, it plummets, and then it recovers during more recent periods where people have been moving a little bit more. And so if you try to align this with lockdown metrics, you see that generally there's more correlation, more synchrony when people travel more, which makes sense. And this is something, it seems, that has been seen in a few other diseases where whenever lockdown measures have been put in place, in particular the foot and mouth disease, so zoonotic infection in the UK. We can also look at spatial structure in the contact and mobility metric, because if we see a spatial structure in the disease data, it could be either because there's a true diffusion of the disease, or just because the drivers of this disease, for instance, the contacts, are themselves very spatially distributed. And that could make sense because different cities within the same state will behave similarly because they are exposed to the same interventions if they are decided by the governor at the state level. But interestingly, we don't see very much of a spatial signature in some of these contact data. I'm just choosing two here. As I said, the commutes are incredibly well correlated across the US. Commutes plummeted after the lockdown and haven't rebounded. And that's true everywhere. Contact duration has a bit more heterogeneity, but the correlation is still around 0.6, 0.7, 7.2 or something. And also, we don't see as sharp as a spatial gradient. I mean, there's a bit of a gradient. It's not as sharp as what we see in the disease data. So we think there's probably a little bit of a true spatial diffusion here that we capture in the RT and in the incidence data. And again, to put this in the bigger context, I'm comparing here COVID-19 with flu. And so, in flu, generally, this is seasonal flu. Generally, you see very high correlation. It's very synchronous across the US. And there's a little bit of a spatial gradient, but really not as much as what we see here in COVID-19, especially if you look at the East Coast. And then the 2009 pandemic had very little spatial pattern when you look at this metric here. So we see a distinctive spatial structure of COVID-19, which is more pronounced than for flu. And it could be perhaps because there's spatial structure in the initial seeding, but also, as I said, that there could be a spatial structure in just a local intervention. So we're trying to tease out those two factors. And if you want to compare COVID versus flu, in particular the 2009 pandemic, which is also the invasion of a new virus, we have very different transmission process. There's a longer serial interval for COVID, an older age structure. I mean, for flu, it was thought for a very long, I think it's still thought that it's children that drive it, and children don't travel very far generally. But also what sets 2020 apart is the huge reduction in travel pattern, in long-range travel pattern across the US. And there are also, in trying to compare those two different disease data issues, right? I mean, we have lots of lab testing for COVID, and we had relatively little for flu. So there's also some measurement error here to keep in mind. So clearly this is ongoing work, right? We don't have the full story here on the spatial structure, but we see that mobility and contacts, particularly contacts, directly affect incidences and transmission rates. We don't see a huge role of local demographic factors. The early dynamics of COVID-19 are very, very tricky to reconstruct because, back in February, March, there was so little testing that the data is really, really questionable. We see a pronounced spatial structure in incidence, which I'm very excited about because it's rare to see in a human disease a spatial structure. I mean, we see it in rabies, for instance, but raccoons don't travel as far as humans. So it's interesting to see it there, and maybe that's a feature of just the very depressed travel that we had. And so we're trying to build a more statistical approach to include immunity, as well as thinking about a mechanistic approach that could try to reconstruct some of those patterns of introduction and diffusion. And with this, I will thank all of my collaborators at the Fogarty International Center, and I'll be happy to take questions.
Thank you so much, Cecile. That was a wonderful talk. Very informative, definitely. We have 2 questions written in the Q&A, so I thought maybe we could start with those. If anybody has additional questions, please write them in the Q&A box. But the first question was asked after the first third of your talk, that was kind of looking at the increases in COVID-19 and how that related to cancer and all the other causes that you list. So the question is there any way to look at increases in non-COVID-19 causes association, so cancer, cerebrovascular, with overburdened healthcare systems rather than possible unidentified effects of SARS-CoV-2? Does that make sense?
Yeah, absolutely. I mean, we try to do that to some extent by, and I went quickly, but we have models where we have both COVID-19 intensity and the strength of interventions together in the same model to try to parse out which is which. The strength of lockdown is not necessarily directly related to how overburdened the healthcare system is. So that would be a really great metric to try to build in if we could. I'm not aware of any indicator of this, but perhaps that's something that, that exists somewhere or that could be derived. But yeah, we don't see any clear association between any of those excess mortality pattern and strength of lockdown. So it has to be something else. So that would be interesting to do. But yeah, if we could get the right indicator.
And then the second question was on the US data that you presented later with Arnott. In your associations between R sub T per US city with mobility / contacts, do you actually estimate the city-specific random intercepts?
Yeah, we do. We have random intercepts in the model. They're just small, and we've also looked at them to see if there was any geographic pattern or if they were tied with density or other factors, but we can't see anything clear there. I mean, other studies have pointed out the importance of population density very early on in the pandemic. I don't think we can roll this out here because it's just so difficult to look at the very early beginning of the pandemic because of data issue, as I mentioned. But I don't think it's necessarily the final word on this.
Do we have any other questions from the audience? People can raise their hand or type it in the Q&A. So I might ask one while we're waiting. So I was kind of interested in, you were kind of looking at contacts in China and kind of the strength of the lockdown or how it was maybe intense at different time periods. And one thing I noticed is that while lockdown was released and contacts were rebounding in older age groups, they were actually, I think if I read the graph right, they were actually always present in the lowest age groups because schools were closed. So I wondered if COVID has, what can you say there about the interplay between age-specific lockdowns, age-specific disease, and how that's showing up in the data? Do you have anything to say there?
Yeah. I mean, clearly contacts have changed a lot for 2020. This was just one time point where schools were not quite open, across China. And so contacts were just, still depressed. So, yeah, I mean, I think there's right now a lot of question about the role of children in driving this epidemic and trying to get more of those very specific contact patterns and align it with disease dynamics in different places can inform this question. I think there's a lot of mixed evidence out there, but those studies are really useful. I think there's also, if you're going to keep children at home, then you're also depleting contacts among adults just as a result, right? Because at least one parent has to stay home. So there's a lot of interaction between actually contacts across the age group because of that. Yeah, but I think we just don't have enough of those really nice detailed contact matrices across enough locations.
Yeah, that makes sense. That makes sense. We have one more question in the Q&A. It says, on one of the first slides, there was an interesting decline in less than 25-year-old mortality in late 2020 to 2021. What is the reason behind that?
Yeah, I mean, it's a great point. And so across the US, there's very, very little circulating except for COVID-19 in terms of pathogens. There's no, some of the big ones are respiratory syncytial virus, paraflu, metapneumo, and those cause a few hundred deaths a year in younger age group, because those are the age group that typically don't have immunity. And so that decline in mortality pattern in under 25 years old could be due to that. I mean, in the same way that we saw those depressed admissions for respiratory causes in South Africa, because they just didn't have any respiratory viruses until those viruses rebounded. So I think the question in the US, as we get out of the lockdown or semi-lockdown that we have here, how much of those other pathogens are going to rebound? I mean, even enteric viruses have been depressed. And so if they do rebound, are the peaks going to be higher? And is mortality, is that going to compensate for the negative excess in mortality?
Wonderful. Well, thank you very much for this extremely interesting talk. We appreciate it very much.
Well, thanks a lot. Thanks for the good questions. I'm going to meet with some of you later on, so that's great.
Dev, is there any closing message or?